Namaste everyone, welcome to my channel. In today's video we are going to be starting with physical geography revision of climatology. So it's actually the second pillar. The first pillar was geomorphology, which we already completed, and now we start with climatology. In today's lecture we are going to be mainly doing everything about atmosphere, pressure belts and wind. So let's get started. Firstly, let's understand the difference between climate and weather. So, climate is a long-term pattern of a weather, and weather is basically very short-term. So, I can ask what is the weather like today. So, it could be rainy, it could be hot, it could be windy, but it is about today. It is about the current time. But climate is mainly an average of over a long period of time. So this is what it is: climate and weather over many years in one specific place. So we can say that in the equator, for example, the temperature is always going to be high, so that is its climate. But if you are in the equatorial area and you see that right now it is raining, so that is the weather of that place at that point of time. If you see that it is not raining but it is very hot and humid, so that is the weather of that place at that particular time. So that is the difference between weather and climate. If we focus on the study of weather, it is actually called meteorology. But when we focus on the study of climate, it is called climatology. So since weather is quite dynamic, we don't focus on that for our exam, we focus on climatology. So let's get started. Now, let's understand what is atmosphere. Atmosphere is a layer of gases that surrounds the earth, and it envelops the earth completely because of its gravity. So it's actually protecting the earth from harmful radiations coming from the sun, and that's actually what is also making it possible for existence of life on earth. So that is what is atmosphere. Atmosphere is like I said, it is enveloped because of the gravitational value. Now since the gravitational value is more at poles, because we understood earlier that the shape of the earth is geoid, so it is a little it's kind of coming out a little bit from the equator. So from the center to equator, the distance is a little bit more than from center to the pole. So because of that, the gravitational value at poles is a little bit higher than that at the equator, which is why the thickness and the density of the layer of atmosphere is different than at the poles than at the equator. So at the poles, the density of the air, or the atmospheric density, is a bit higher, since the gravitational value is high, so it pulls down more towards the surface. And at the equator it is a little bit less dense, which is why, since it is pulling down, the thickness of the layer of atmosphere is more at the equator than at the pole. So right here I have marked that the layer is denser and thinner at the poles than at the equator. That is about the layer of atmosphere. Now, the layer of atmosphere is basically composed of mixture of gases, which is something that we also call it as air. And when the air moves horizontally from one place to another, it is called wind. So I've just introduced the concept of wind and air, but we are still going to focus on the atmosphere for a bit. Now here is the composition of atmosphere. When I say that it is mixture of gases, let's understand which are the gases that are there in the atmosphere. Now the most abundant of the gases in the atmosphere is nitrogen, which is some 78% in the atmosphere. Nitrogen, as we all know, is used in the fertilizers. I'll just write it down over here. It's used in fertilizers, and it helps in growth of the plant. So that is the main use of nitrogen. Oxygen is we all know that respiration cannot happen without oxygen, so life would not be possible without it. So right here, respiration is one of the main uses of oxygen. Argon is used in, it's actually an inert gas or a noble gas. Such gases do not generally react with other elements or other gases, which is why it is used in light, in the bulbs and the tube lights. So it's an inert gas. That is something that we need to remember about this, and it is used in tube lights and bulbs. And then carbon dioxide. Carbon dioxide is useful in maintaining the temperature of the earth. So we all know that there is a greenhouse effect which is happening, which is what keeps our earth a little warm, and that is the only reason that we are able to survive in this weather, because otherwise, if not for carbon dioxide and other greenhouse gases for that matter, the heat would not stay trapped in the earth. So the days would be extremely hot and the nights would be freezing cold, because there is nothing to trap the heat within the atmosphere. So that's what the role of carbon dioxide is. It's a greenhouse gas. So these are the layers of the atmosphere. This is something that we need to understand very thoroughly. So the first topmost layer of the atmosphere is troposphere. Right here, if we see that the first layer is troposphere. Troposphere lasts up to some 12, on an average it is said to be about 12 kilometers from the surface of the earth, but at the poles it is a little lesser, somewhere around 8 to 9 kilometers, and at the equator it is a little bit higher at some 17-18 kilometers. But on an average it is said that it is around about 12 kilometers. That is the layer of troposphere. Troposphere is the place where all the weather phenomena happen. So all the rainfall, cyclones, everything that we experience on a daily basis, all of it happens in troposphere. So it's important for that. Troposphere actually ends at a point which is called tropopause, and we actually had to segregate because there is a very vivid difference between all the between how the temperature and how the density and how the pressure acts in all these different layers. So let's understand this. Now, what is a normal lapse rate? What happens is, as in when we go away from the surface of the earth on troposphere, the temperature of the region, the atmosphere, the temperature, it reduces. As in when the height increases, the temperature reduces. At what rate? On an average, the temperature reduction is up to is about 6.5 degree per kilometer, and at tropopause the temperature reaches up to minus 60 degrees Celsius. So this is the normal lapse rate as in reduction rate. So normal lapse rate is 1 kilometer, for every 1 kilometer 6.5 degrees Celsius temperature drops, as in when we move away from the surface of the earth. So that is troposphere. The next layer is that of stratosphere. Now stratosphere actually starts right after tropopause, and from tropopause to some 30 to 35 kilometers on in the stratosphere is the ozone layer. Now, what is the importance of ozone layer? As we have studied, years ago in school also, that ozone layer is responsible for preventing the ultraviolet rays from entering the surface of the earth. So, entering the atmosphere of the earth. So, mainly in the troposphere area where it can affect us. So, how does it do that? So, if we see right here is an oxygen molecule. When ultraviolet rays are, energy, when it says energy over here, ultraviolet rays, when it hits the oxygen molecule. So oxygen is always written as O2, if you know. So when it has it has two oxygen atoms, so both the atoms it kind of breaks apart because of the extreme heat that it receives, and it can what can happen is that it can meet the another oxygen molecule. So the one single atom, a free oxygen atom, is not very stable. So it will immediately want to react with something else, and if it finds another oxygen molecule, it might react, and O3 will be formed, and O3 is what is ozone. And what happens sometimes is that, because of the ultraviolet rays, the rays can also fall on ozone, and it can again break apart, and then again it can turn into oxygen, and and one free atom, and it can kind of keep going back and forth at a very faster rate. When this happens, see right here, it is it gets it is continuously being interconverted, and it reacts very fast. So when that happens, what happens is that the ultraviolet rays that are coming, that is the UV radiation gets converted, that energy gets converted into thermal energy, and it gets used up right there, and it gets converted into thermal energy, and it doesn't reach the surface of the earth. When that happens, this actually which thermal energy basically increases the temperature of that area, which is why, unlike troposphere, as there is no normal lapse rate. So in stratosphere, as we go up from tropopause to, as we kind of keep going up, because of the thermal energy released at the ozone layer, the temperature increases instead of reducing. And from 0 degrees, from minus 60 degrees at tropopause, at stratopause it can reach up to 0 degrees. So it is increasing with height. Another important fact about stratosphere is that this is exactly where airplanes fly. Airplanes fly in stratosphere because the weather phenomena is not happening here, and that is why the path is quite clear, the visibility is quite clear, and the pilot can easily navigate from one place to another, which is why this is a preferable area. Now, while we are doing ozone, how ozone layer prevents UV radiation from entering the surface of the Earth, let's also understand how the depletion of ozone layer happens because of chlorofluorocarbons. So, as we know that chlorofluorocarbons is a gas which is released from refrigerators and air conditioners, and when that happens, what happens? There are 3 atoms of chlorine. So this chlorine is much more reactive with the oxygen atom than the other oxygen molecule. So when the sunlight is hitting, and there is there are 3 oxygen atoms, there's an oxygen molecule, this chlorine is going to snatch up one of the oxygen molecules, and it is going to form chlorine monoxide right here. And then again it might kind of release it and allow to form another O2, and it will again become free and find another oxygen molecule. So what happens in this process is that it is not going to allow the conversion from oxygen to ozone, and it will not be allowed to use up the ultraviolet radiation. So it is going to create a hole in the ozone layer, which exactly means that it is not going to allow the natural process of ozone and oxygen interconversion, which actually prevents the ultraviolet radiations from entering the atmosphere. So that's how it is harmful. So this was the process of it. So we studied stratosphere so far. The next layer is the mesosphere. Mesosphere is again after stratopause. When it goes up, it is like normal lapse rate, but it doesn't exactly have this minus 6.5 per kilometer. But in here also, as you go up, as the height increases, the temperature keeps falling down. So the stratosphere was up to some 50 to 60 kilometers, and then above that mesosphere is somewhere till 85ish kilometers. So that's how long, that's how far mesosphere is. Mesosphere is also the place where it is kind of the last area where normal gas molecules that we were able to find in troposphere and stratosphere will also be visible. Like above mesosphere, such gases, full molecules of gases, it will be very difficult. So this is actually the last place where gas molecules will be available. Mesosphere is the coldest layer of of all the layers of the atmosphere. So here, as mesosphere ends, by that time, somewhere around minus 90 degrees or so, the temperature would be there. Another important point about mesosphere is that since it is the last place where the gas molecules will be present, there will be there's still going to be some chance of friction. So what happens is, this is the place from where meteors, right, if you see the diagram here, meteors are formed in this layer. So what happens is, what are meteors and meteorites and meteoroids? Let's get to that. So asteroids are actually found in the belt between Mars and Jupiter. Sometimes a small piece of rock from that huge asteroid might break apart, and because of the gravity of the Earth, it might get attracted and it might enter the atmosphere of the Earth. Now, the small rock that has broken apart is called meteoroid. As long as it stays in space, it is still called a meteoroid. But if it enters the atmosphere of the Earth, when it reaches mesosphere, that's where there are some gases, and it might create friction because as the meteoroid is moving. So because of that, it will catch fire. Now this phenomena where meteoroid is entering the atmosphere, and it is because of friction it is catching fire, it appears like a shooting star, and this is what is called a meteor. Now, most of the times, the meteor ends up, burning off completely before it reaches the surface, and that's what happens in most of the cases. But sometimes, if the piece of the rock that has entered is too big and it does not completely burn off, that's when it might hit the surface of the Earth, and when that happens, it is called a meteorite. So meteoroid is when it is in space, meteor is when it is catching the fire, and meteorite is if it hits the surface of the Earth. So that was about mesosphere. Then after mesosphere, above that is, here it says it is thermosphere. Now thermosphere has actually two components. The first is ionosphere, and the second is exosphere. So as such, from our books, it is said that thermosphere, I know exosphere is also part of the thermosphere. Now why is it called thermosphere? It is called thermosphere because here again, with increasing height, the temperature is going to increase, because now the distance has reduced considerably from what it was there, as compared to when it was troposphere, distance as in distance from the sun. So what happens in ionosphere, that here there are no you can't find full molecules. As I said earlier, that mesosphere is the last layer where you can find full molecules of gas. Here we might find some free radical atoms that might be there, and these atoms, when they get hit by the radiation, when there is external energy, it might break apart, and some electrons might escape from the full formed atom. So it something of this this is something that might happen, that because of the energy in bombardment on it, an electron might escape, and there might be free radical electrons kind of found in that region. The use of that is that such radical electrons is what is going to help in reflecting the radio waves. So right here, if we see that if there is a this is ionosphere, and in ionosphere also there are three layers that have been divided. The D layer is the closest to the Earth, and from here, if very small frequency radio waves, AM waves, can be reflected, and E is above that, and F is the last, it's the farthest. After that, if we want TV waves or something, if we want to reflect that, we might have to go to satellites, which would be outside of ionosphere. So it might be in the space, it might be outside the Earth's atmosphere. So this is actually the use of ionosphere. Ionosphere, it is called an ionosphere because this process that I mentioned right now, that energy is hitting an atom, and because of that an electron is getting separated from it. this process is called an ionization. And since ionization happens in this layer, that is why this area is called ionosphere. Now, exosphere is also a part of thermosphere. In exosphere, we can find the lightest of gases like helium and hydrogen, but that's about it. You can't find any other full molecules or any atoms over here. So that is exosphere. It is part of the thermosphere, which means that as the height increases, the temperature is also going to increase. So this is the segregation of it. Now we studied troposphere, then we studied stratosphere, and then we studied mesosphere. The three of them combined is actually called homosphere. It is called homosphere because it is, the composition is still quite homogeneous in a way that we can find gas molecules in this region. Whereas above that, everything which is the ionosphere and the exosphere, you cannot find such homogeneous composition, which is why it is called heterosphere. Heterosphere, like I said, is also known as thermosphere. So after this, we actually study a little bit about greenhouse effect, as we already did the use of carbon dioxide earlier. So what is greenhouse effect? Now, sun releases its energy in form of short wave radiation. So if we see that the frequency is quite high of this particular this wave, it's very very fast and it's coming, this is what is called short wave radiation. And generally part of this short wave radiation gets reflected back to the to space because of the clouds. That's what reflects back. The glaciers reflect it back, but some portion of it gets absorbed in the earth absorbs this, gets heated up, and it releases this energy back eventually, not in form of a short wave radiation but in form of a long wave infrared radiation. So this is something that we might have even noticed through common sense, because because of the sun, the earth heats up fast, but while cooling down, it will not instantly cool down as soon as the sun goes down. It is going to be it is going to take a while before it cools down. So sometimes, during the summers, we can see that even at 8 o'clock or 9, when the sun has completely set and it's night time, then also the ground might be a little bit hot, which means that the earth is releasing the radiations, but it is taking some time to do that. And this is what is called long wave radiation. So these are long wave radiations and these are the short wave radiations. Now the atmosphere that gets heated up is actually heating up not because of the short wave radiation, but because of the Earth's long wave radiation. Now these long wave radiation, it gets trapped in the atmosphere because of the greenhouse gases. The greenhouse gases cannot preserve the short wave radiation. It gets reflected back immediately. The only place it gets absorbed is the surface of the earth, whereas the long wave radiation, it gets trapped in the greenhouse gases, and that is what keeps the atmosphere or the temperature on the warmer side. And because the greenhouse gases are increasing rapidly because of excessive use of vehicles and industries and everything, and because of that, since it is more carbon dioxide is getting emitted every day for that matter, the more of the heat gets trapped, keeps getting trapped in the atmosphere, and because of that, global warming is occurring. So that is what global warming is. Now this is the graphical representation of layers of atmosphere. This diagram is very important in the sense that if a question is asked on the different layers of atmosphere, we have to draw this exactly the way it is shown in this figure. So let us understand how it is, what it is trying to depict. Here is the altitude, which means that the height is increasing. So from 0 to 20, 30, 40, 60, 80, 100, this is in kilometers. And this is the temperature in degrees Celsius. So earlier we understood that in the troposphere, the as the height increases, the temperature reduces. So it is said that, at some place where there is 20 degrees Celsius, from there we are starting to observe. So here it is 20 degrees Celsius and the height is 0, if we see here. From here, as in when it goes up till some 18 to, here it is marked at 12 only. So till some 12 kilometers, the temperature is reaching to somewhere around minus, 50 to 60. It is between minus 50 to 60. So right here, if we see, that is what is the first line. Then here is a space because of tropopause, so the temperature more or less remains the same in this area. And then from tropopause till the end of the stratosphere, the temperature keeps increasing and it reaches, if we mark right here, if we see, it is exactly at 0. So from tropopause to stratosphere, the temperature reaches up till 0. So it stays 0 for a bit in till stratopause. And from stratopause to mesosphere, if we see right here, it is reaching minus 90. And this is what I said, that it is the coldest layer. And after that, mesopause is there. And after mesopause, thermosphere and ionosphere, here it is increasing with height and it is going to keep increasing. So this is the graphical representation that we have to remember and we have to learn. Okay, so we are done with the composition of atmosphere. Now we move on to the wind system. Now wind, generally how it moves from high pressure to low pressure. So it needs a pressure gradient. Gradient means difference. It needs a pressure difference. So how it happens? So suppose there is a piece of land, and here because of the temperature, the wind around here, it gets heated up. And since the wind is heating up, as we understood earlier, that the wind gets heated up because of the long wave radiation released from the earth. So the air gets heated up and it rises above in form of a convection current. Since it is rising above, here there is less temperature, here there is less pressure, because whatever wind was there, whatever air was there that was exerting pressure on that landform has moved up, and so the pressure of this area has reduced. This is the case over here. At some other place, because of the wind, that is the air that is there at height might become very cold, and it might not be it might not be able to hold itself there, because as the air is cold, it might be very dense and it might kind of start sinking down. So if it is sinking down here, at this place where it is sinking down, the the pressure might be very high, because it is exerting the pressure on the land. Now here there is high pressure and here there is low pressure, and wind always moves from high pressure to the low pressure. So it is going to move in this direction, and this is what is called wind. This upward movement and this downward movement is not wind, it is actually currents. Wind is only when there is horizontal movement, as I explained earlier. So let us understand something about high pressure and low pressure. When there is high pressure, we saw that the wind, the air that was there at high pressure, it is trying to move away from that place towards low pressure. So the wind is going to move away from high pressure, which is why this place is called diverge. There is a happenstance of divergence in high pressure area, whereas in the low pressure, the wind is going to try coming from all the direction, which is why there is which is why there is convergence. So at low pressure there is convergence, and at high pressure there is divergence. This is a phenomena that also we need to understand, although we will do it in detail during studies of precipitation and cloud formation and everything. Today we are not going to get into it, but the basics of it is that as the air heats up and it rises, or it rises for any reason for that matter, cloud formation happens and precipitation or rainfall occurs. So when such rainfall is happening, it is actually called instability conditions. Whereas if the air is descending below, it's descending down towards the surface of the earth, clouds will not form and rainfall cannot occur in such areas, which is why such areas are where deserts will be formed. and when there is clear sky, that is what is called stable conditions. So this is the basics of wind system. So what we need to understand from these basics is that we know that there is a certain kind of climate of different areas, which means that there has to be a permanent kind of wind system, which also means that there are going to be places where there is going to be permanent low pressure and permanent high pressure. So let us, if we understand those places and if we understand the direction of the wind, we are going to be able to predict a lot of things regarding the climate, the vegetation and everything. So let us try and understand the pressure belts, or the low pressures and the high pressures in the wind system. So let's get on to it. So let's get started in understanding the wind circulation and how the wind systems work. Now, as we had studied earlier, that there's going to be direct insolation of sun on the surface of the earth around the equator area, which is why the temperature of the equatorial region is going to be very high. Now, as the equator area is receiving direct sunlight for a lot of time, the surface of the earth is going to heat up, and it's going to release the long wave radiation, which is going to heat up the air above the surface of that area. And this air, as it gets heated up in form of convectional current, it is going to rise above. Now, as it rises above, this place is going to form a low pressure area. Since it is a low pressure area, wind is going to come from all the direction, which means that there is a high pressure area pretty close to it. Now what happens is that since this convectional current, it of the hot air, it rose up. As the air is rising up, after reaching a certain height, it is going to start cooling down, and when it cools down, it is going to start getting denser and denser, and it is going to want to settle down after reaching at a certain height. So after that, it is going to come down. And generally, as it has been observed by different geographers, so FERREL was the first one to observe that actually. So what happens is that it actually settles down at somewhere around 30 degrees of latitude. So 30 degrees south as well as 30 degrees north. So equator is 0, which is where there is low pressure. And since it is landing at around 30 degrees, this place is what is going to have a high pressure. So this, from high pressure to low pressure, the air is going to flow from both the directions, from the southern hemisphere as well as from the northern hemisphere. So this is actually the cross-sectional form of the surface of the earth. Right here is the southern hemisphere, this is the northern hemisphere, and this is the 30-degree north latitude. Here the wind is settling down, which is why there is high pressure, and here the wind is rising because of the high temperature. Now here as well, comparatively, the temperature is going to be high, but because the wind got cooled down, it is not going to be able to stay up anymore, it is going to settle down. This is actually, even though the temperature is comparatively higher than the other regions over this side, from the higher latitudes, it is still going to have high pressure, and that is why it is unnatural, because if the temperature is high, it should ideally have low pressure, but it is not, which is why this is called dynamically induced high pressure area. So this is dynamically induced high pressure. Now what happens at this area is that this is dynamically induced high pressure. Now at the poles, the temperature is anyway extremely low, and here there is going to be a natural high pressure. So at the pole there's going to be a natural high pressure. Here also there is this is dynamically induced high pressure. So there has to be a low pressure in between. So it was observed that around 60 degrees of latitude there is a low pressure. How? That from polar region here, since a high pressure is forming, the wind is going to it is going to diverge, as we studied earlier that at high pressure there is divergence. So it is going to diverge at this place, at a certain place where there is temperature is a little more as compared to the poles. So here there is going to be divergence, and air is going to come from the poles to this area around 60 degrees latitude, And from here also, again, because of high pressure, there is going to be divergence, and air is going to come from both, it's going to go towards both directions. It is also going to come in this area. Now since the air is coming in this area, what happens is that, this air is going to be a little colder and this is going to be a little warmer because it is coming from high temperature area. The warmer air is going to as according to its nature, it is finding space, so it is going to rise up in convectional current, and it is going to rise up in this manner. The colder air, now reaching this area, it has certainly gained a little bit of temperature, but it is still not as hot as this, and it is not, both the airs are not going to get mixed up because they are of different temperature, which is why this air is going to rise up easily. But this air, it is going to need an extra push to rise up. That it gets in form of a centrifugal force which it receives from the rotation of the earth around its axis. Because of that, it kind of pushes up, and that along with the force of this this bit of wind rising up. So because of both the forces together, it is also going to rise up eventually, and convectionally, and then eventually it is going to come down to the poles, and it is going to reach right here again, and that's how a high pressure is formed at the poles. So this is how the winds are circulated. So these are actually the permanent places where the high pressures and low pressures are found. So this is equatorial low pressure, this is subtropical high pressure, this is subpolar low pressure, and this is polar high pressure. Now this kind of circulation that is happening right here, this circle that has formed, is actually called Hadley cell. So Hadley was the first person to observe this kind of a phenomena. However, his theory was that after the convectional rise of the air over here, it directly travels to poles, and from poles, here there is high pressure, and it directly travels all the way to equator. But it was FERREL who discovered that this is not the direct, from here it doesn't directly go to poles, it actually settles down here, and then there is another high pressure formed in between and another low pressure formed in between, and that is how the entire wind circulation works. And this was actually introduced by FERREL. So the first cell is named after Hadley, next is FERREL cell, and the third cell is called the polar cell. So if we see here, this is the, right here if we see, this is the Hadley cell, this is FERREL cell, and this is polar cell. Both of these together, these both are, this is equatorial, this is high pressure and low pressure, and the wind is rising up and it is kind of circulating. So this is Hadley cell, this is also Hadley cell. Here this is the FERREL cell, and this is the polar cell. Now let us understand the concept of isobars. So iso equals to same, and bars is it's actually used for barometer is what is used to measure pressure. So isobar means similar pressure. So if we mark points where there is similar pressure on the surface of the earth, and if we kind of draw an imaginary line through all those points, such a line is called an isobar. So if there are two different isobars, the pressure gradient is always going to be perpendicular to that, to two different isobars. As I said, suppose this is high pressure isobar and this is low pressure isobar, it is going to the gradient is going to be in this direction. So the wind is also going to want to flow in this direction. Because of Coriolis force, it is going to deflect a little bit. But the important thing to know is that pressure gradient is always perpendicular to isobar. Another important concept that we need to remember is that if the isobars are close to one another, the slope is going to be more. So as close as they are, so suppose if this and this, if this is the if we understand in terms of water, so if the slope is like that, this point and this point is going to be a little bit far away. But if it is like this, these two are close to one another, then this is going to be much more steeper. So the slope is higher. So similar kind of logic works here, that if the isobars are closer to one another, the slope is going to be more, and because of that the speed of the wind is going to be very high. This concept is going to be useful during understanding cyclones, but we are going to do that in the next video. Now let us understand the Coriolis force. Now Coriolis force is also associated with the rotation of the earth. So what happens that the wind that is going to want to travel perpendicular to the isobar, so it is going to want to travel in a straight direction like this or like this, whatever the direction of the wind is. It is not going to be able to do that, and it is going to deflect a little. So as such, we are not going to get into the theory of Coriolis force because it is not relevant for our exam, but how Coriolis force behaves is what we need to understand. So if the wind is flowing in the northern hemisphere, it is going to deflect to the right of its direction. So if the direction of the wind is in this manner, it is going to deflect towards its right. So if it was like this, it is going right, and if it is coming like this, you can't say that this is left, because this from, if you need to kind of turn it around, so it is going to be the other way around. If we check from, if you are standing here and if you see from here, then the direction of the wind is here, and from here if you see that this is going to be your right. So this is why it is said that it is on the right. Whereas when it comes to the southern hemisphere, the wind is going to deflect towards the left of its direction. Now, how do you determine its direction? You have to see from the high pressure point, because its direction is going to be determined from the high pressure to low pressure. So if this is where the high pressure is occurring and it is going in this direction, it means from here you have to see that it is going to go deflect towards its left. So if we see that the wind is coming from here and it is in this direction, it is deflecting towards the left, and if it is here again, it is deflecting towards the right. So this is the easier way to understand. So north equals right and south equals left. So this is the easiest way to remember Coriolis force. Okay, so let's understand the pressure belts and the winds. So most of it we've already done a little bit. So this is the equatorial area, and this is the permanent low pressure area. From here, as we said that, and this is the subtropical high pressure area, as we said earlier, around 30 to 35, between 30 to 35 degrees latitude. North and south, there's going to be subtropical high pressure area. Now from high pressure, the wind is going to want to flow towards the low pressure. So it wants to flow in this direction, but because this is the southern hemisphere, it is deflecting towards the left. So the wind is coming in this direction like this. And similarly, in the northern hemisphere, it is going to want to deflect towards right. So it is going to come in this direction. If you see, this is the starting point of from here you have to see left or right. This is the high pressure, this is the low pressure. So yeah, if we see from here, this is the, this is what is its right. So this is how is the, so these winds, the first, the winds coming from the subtropical high pressure area to the equatorial low pressure area, these winds are called trade winds. Trade winds are actually coming, if we see, they are actually flowing from the east to the west. The general direction is east to west. Now, one thing to remember about the names of the winds is that a wind is always named from the place it originates and not from the place where it is going to. So its destination is not counted, but its origin is counted in its name. So since it is coming from the east, these winds are also called easterlies. These are subtropical high pressure to equatorial low pressure winds, and these are the easterlies. They are also called trade winds. They are part of the Hadley cell. So this is the first cell that we understood right here. This bit from equatorial low pressure to subtropical high pressure. This wind Hadley cell, that is what is the um, trade winds or the easterlies. Now, if we see properly that since it is coming from here, it wants to come from here north to south, but because of the Coriolis force it is deflecting from east, a little bit from east to west. So if we accurately mark its direction, it is actually coming from northeast to southwest in the northern hemisphere, whereas it is coming from southeast to northwest in the southern hemisphere. So that's how it is marked. Now, as we understood earlier, that high pressure areas are big. These are the areas where the wind is descending. So that is why cloud formation doesn't happen, and that is why a lot of deserts are found in this area. Another contributing factor to the deserts is these winds, because these winds actually so I'll explain it from the map. So if we see right here, so this is the Tropic of Cancer. So right here would be somewhere around 30 degrees latitude. So if we see here, there's a desert. All of these areas, they all fall under subtropical high pressure area. And here as well, if we see this area, this desert, all of these fall. And most of them are actually found on the western end of the continent. The reason for that is the trade winds or the easterlies. Now what happens is that since the easterlies are coming like this is their direction, easterlies, and here they are also coming from the east and they are in this direction. So what happens because of that since this is coming from here, there might be some rainfall seen in this area, but there might be no rainfall as and when it reaches the end of the landmass. So here if we see that this part there might be some rainfall, but here again there will be no rainfall, so again desert. Now since the wind is flowing from this direction, the water, little bit warmer water that is there on top of the ocean in this region is going to get carried away with the wind like this, along with the wind. And so again here there might be rainfall, but here there is no rainfall also. There is no cloud formation, and the fact that as the warm water is going away, the cold water that is there in the depth of the ocean, it tries to come up because the top layer of the warm water moved away, and the cold water that was there, it comes up, and because of that the evaporation also doesn't happen in this region. So even the localized rain does not happen, and that is why these areas have deserts. So that was one concept that was associated with trade winds. So after trade winds, we move to the next area, which is from subtropical high pressure belt to the subpolar low pressure belt. Here what happens is that this is the high pressure and this is the low pressure. So the wind is going to want to go in this direction, but since it's the north hemisphere, it is going to deflect towards right. So this is the direction if you see. And in the southern hemisphere, also subtropical high pressure to subpolar low pressure, the wind is going to want to come in this direction, but since it is southern hemisphere, it is going to deflect to its left. So right here, this is the direction of the wind. And these winds, since if you see the direction of them, they are going from west to east. So that's why they are called westerlies. So these are westerlies. Southwest to northeast, this is southwest, this is northeast. So that's the direction in the northern hemisphere. And in the southern hemisphere, it is northwest. Right here is northwest to southeast. So that is the direction in the southern hemisphere. The speed of these winds is actually much more in the southern hemisphere, because if we understand through map, so it will be somewhere here. This is the area of westerlies. So somewhere here. Now if you see that this area, it has a lot of landmass in the northern hemisphere, but it does not have much of a landmass in the southern hemisphere. Because of that, in the southern hemisphere, in the northern hemisphere, this landmass is going to cause some sort of barriers, but here there are going to be no barriers. So the wind is going to flow at a very fast speed. So because of that, as we go below, if we see that in the higher latitudes, so if we see, from at 40 degrees south, these winds are called roaring 40s. At 50 degrees south, it is called furious 50s, and at 60 degrees south, it is called shrieking or screaming 60s. So because of the fact that the winds are at flowing at a very fast speed only in the southern hemisphere, because of very limited landmass, these are the names for westerlies. So if all of these are mentioned, they are all westerlies. Roaring 40s, furious 50s, and screaming or shrieking 60s. Next are the polar easterlies. Polar easterlies are flowing from polar high pressure area to the subpolar low pressure area, and these are again the easterlies, because they are coming from east to west. They might want to go in this direction, but because it's the northern hemisphere, it is deflecting like this, and in the southern hemisphere, it is deflecting towards the left. So these are the important pressure belts and wind system. I actually forgot to mention one thing earlier, that in this, as we said, that this bit, since this part was dynamically induced high pressure, similarly this rising up is also it is not temperature induced, so that is also dynamically induced current. It is not a natural current formed because of temperature. It is dynamically induced current because of the centrifugal force and the force of the rising up of this relatively hotter air. So that's something that we forgot to mention earlier. Anyways, moving on to the next concept is the intertropical convergence zone. What is ITCZ? So if you see right here in this diagram also, ITCZ is written right here. So what is intertropical convergence zone? We understood earlier that convergence zone happens in low pressure, because if there is low pressure, the air is going to want to come from all the direction towards it. So convergence zone literally means that it is a low pressure area, and intertropical means that it is between the tropics. So if we understand this equatorial area where there is low pressure permanently, that is what is called ITC, there are intertropical convergence zone. So as such, in theory, equator region is going to always be ITCZ, but sometimes ITCZ shifts because of the revolution of the earth as well, because during the summer solstice and the winter solstice, the sunlight, the direct sun rays are going to fall on Tropic of Cancer and Tropic of Capricorn, and at that time, the temperatures over there, the surface of the earth over there is going to get heated up more than the at the equator, and that is where the low pressure is going to be there, and that's where the ITCZ is going to be there. So, if we see right here, it is saying that July ITCZ is somewhere in this area. So this is around summer solstice, and the January ITCZ is somewhere around this area, which is around winter solstice. So, it kind of keeps changing, but for this physical geography purpose, we will only focus on this much. This will be done in detail in the Indian geography version, because that's how even Sudarshan Sir taught. So I'm going to leave it for that as well. So ITCZ is associated with instability in weather. So wherever there is ITCZ, the wind is going to the air is going to get heated up, and it is going to convectionally rise. And as the air rises, it's going to form clouds, and eventually it's going to cause rainfalls. And that when there is rainfall, it is called instability, whereas when there is no rain, it is called stability. Now let us understand some other concepts. So what are doldrums and horse latitudes? Now what happens is that at the ITCZ area, or at the equatorial low pressure belt, the air is, if we see here, if we understand again from the same diagram, that here the air is rising in this direction, and then here we can find wind. Here also we can find wind. So if you are standing here at this place, you will find wind. But if you are standing here right in the middle of the equatorial low pressure area, or right at the ITCZ, here we can find rainfall, but there will be no wind that we can feel because all the air is rising up. There is no horizontal movement. So this place where there is no horizontal movement of air, such a place at the equatorial area is what is called a doldrum. So right here it is mentioned in this place. This is a doldrum. Similar case happens even in the high pressure area at this place. Here also there is no horizontal movement. Here also, if we see that the air is descending, but there is no horizontal movement observed here. So this place is what is actually called horse latitudes. There's a story associated with it that when the merchants, when they used to travel in the ships, and they used to carry horses in them, but because their ships would not move from this area because there is no wind to support its movement, they would want to reduce some weight, and they would kind of throw the horses that they brought along with them in the sea and reduce the weight, and the fish and the ship would start moving again. So because of that story, this is it's called horse latitudes, but it's actually subtropical high pressure belt. That is what is called horse latitudes. The difference between horse latitudes and doldrums is that doldrums is associated with low pressure area where and instability, because there is ITCZ there because there is rising of air. So instability and low pressure area, but the winds are calm. There is no the wind is not there, so calm conditions in terms of winds. However, horse latitudes, they have high pressure area because the wind is descending over there, but it has stability also because there's not going to be any rainfall, because there's no cloud formation, because wind is coming down and it's not rising up. And again, there's also still calm conditions in terms of wind. So if I say that there's calm conditions and there is instability, it is not contradictory, because instability is in terms of rainfall and calm conditions is in terms of wind. So these are horse latitudes and doldrums. Moving on to the types of winds. So the winds are classified into three types majorly. The first is permanent winds or the planetary winds. These are the easterlies and the westerlies. So the trade winds, the polar easterlies and the westerlies that we studied earlier at the permanent high pressure and the low pressure belts. These are the permanent or the planetary winds. Now, other than these winds, there are also some seasonal winds, which are the monsoon winds and the other kind of winds that change their direction as per the season. However, this is going to be again covered in a much more comprehensive manner in the Indian geography. So I just like Sudarshan Sir, I'm also not going to cover in this video. I'm going to do it in the Indian geography. And the final type of wind is the local wind. So we are going to study the local winds now. So in local winds, the first kind is the land and the sea breeze. So what is the land and the sea breeze? Now, when in the local region, in this suppose localized area, if we just consider that much, there's some sea and there is a land mass. So when the sun rays, they kind of release their energy in form of shortwave radiation, as we studied earlier. It's going to heat up the land much faster than it is going to heat up the ocean. So because of that, the ocean is going to be a little bit cooler, and so it is going to have high pressure here. And here, since the land is getting heated up, it is going to have low pressure, and the wind flows from high pressure to low pressure. So this is how the wind is going to come, and then it's going to rise up from here, and this kind of current is going to form. So this is what is the sea breeze, because it is originating from the sea. But at the night time, at the same place, on the same day itself, the land is going to start cooling down at a very rapid pace. compared to that, the ocean is going to take a lot of time cooling down. So land is going to become cold and the ocean is going to become warm. So the land is cool and ocean is warm. So here there is high temperature, high pressure formed, and here there is low pressure formed. So the wind is going to now blow in this direction, and it is, going to rise up from here, and again this kind of current is going to form. So it is often said that the air pollution is often very less in the coastal areas, because all the pollution in the air that is accumulated throughout the day, at night that air is going to flow towards the sea in form of the land breeze, and the air is going to get, that is going to again move ahead, and in the morning time we are going to get fresh sea breeze, and that's exactly how the pollution is low. That doesn't mean that pollution is happening less, but it just means that the nature has its way of taking care of it. But if there is no coastal area, like the landlocked capital of ours, Delhi, this phenomena is not going to happen. But in Mumbai, this is going to happen, and the pollution level is going to be quite less. So this is land and sea breeze. Next is mountain and valley breeze. Now in mountain and the valley breeze, what is going to happen is that in the mountains, if we see that the slopes are going to get heated up faster than the valley, because it is at a better proximity from the sun than the valley. So these are going to heat it up faster, and because of that, here low pressure is going to form, and in the valley there's comparatively high pressure. So that is why the breeze from the valley is going to flow towards the slopes, and that's why there's, if we see that the direction of the wind is in this side, in this manner. So this is actually called valley breeze because it is originating from the valley. And in the mountain, for the mountain breeze at night time on the same day in the same place, what is going to happen is that the slopes are going to cool down faster, just like the land and the sea breeze, that the slopes are going to cool down faster and the valleys are going to take time to cool down. So here there is high pressure and here there is low pressure. So this is the direction in which the wind is going to flow, and this is actually called mountain breeze. This is why the people in mountains prefer to live on slopes, because at night time this cool mountain breeze is going to freeze them off if they live in valleys. So they prefer to live in the in the slopes, because here it doesn't get too cold, and in the daytime when it is going to get actually very hot, at that time cool valley breeze is going to come and it's going to suit them. So the settlements are generally on the slopes and not in the valley. Now there are specific names to valley and the mountain breeze. So the valley breeze, the breeze that comes from the valley to the mountain top or the slope of the mountain, is called anabatic winds. So how we remember is how Sir also made us remember, is that we stand on the top of the mountain and we say that tu bhi ana upar, ana. So ana is anabatic. So that is how he made us remember. And the other is the katabatic winds, where the mountain breeze, where the breeze is going from the mountain slope to the valley, that is actually called katabatic winds. Now there's a special phenomena that happens in the katabatic winds. What happens at night is that this cold wind that was there on the slope, it is flowing towards the valley. Now since this valley is comparatively hot, and that is why there is low pressure formed here, this cold wind is going to come from top to bottom, and that's why this cold air is going to be here, and it is going to push the hot air above. Now generally in troposphere we saw that there is a normal lapse rate, according to which as the height increases the temperature should reduce, whereas here the cold air is at the bottom whereas the hot air is pushed above, and this is actually called temperature inversion. So temperature inversion happens in many cases, but this is one of them, and this is what is temperature inversion. It is actually opposite to the normal lapse rate. Okay, so these are the important local winds. Apart from that, there are certain local winds across the world which we need to remember. I have actually listed them all down right here, the warm winds and the cold winds. However, I'm also going to do mapping of these winds so that it is easier to remember. So let's get started with the warm winds first. The first wind that I'm going to mark is in this region of the United States, and it is called Chinook. Chinook is also called as a snow eater. I've actually written down its data here. It is warm and dry wind, and it is in the Rockies region. So what happens is that there's a mountain here, and for example there is this wind that is coming from this area, and here it causes rainfall because here there is ocean, and because of that it is carrying a lot of moisture, and here it is causing all the rainfall. But when it reaches in this region, it has become completely dry because this is the rain shadow region. Here is the rain shadow region, and here when it reaches, it is dry and it is warm, which is why whatever snow is accumulated in this area, it is also going to melt that off, and that is why it is called snow eater. So this is some of the extra information about Chinook. So the first one is Chinook, as I said. The next wind to remember is, which is similar to Chinook actually, is found in Switzerland, and it's, I guess, somewhere around here. I'm just going to mark, and it is called Fawn. It is in the Alps. It behaves in the exact same manner as Chinook, but it is not called snow eater because it is just different name. But yeah, it behaves in exactly the same manner. So Chinook and Fawn. The next wind is black roller. That is actually found in the plains of Great Plains of the United States of America. So that is black roller. Another important wind, warm wind again in the US, is in the California region, which is Santa Ana. So these are the important winds in this area. Now there are some important winds in Africa region. So in Africa, from the Algeria region, there is this wind which blows, from Mediterranean Sea to Italy and other European countries. So what happens is that there is a lot of wind blowing here, and here there is Sahara Desert, as if we all know. So it carries a lot of red sand from the Sahara Desert, and it crosses the Mediterranean Sea, and in Italy it causes rainfall. And in that rainfall, it drops all the red sand it has carried with it from the Sahara Desert, and that is why that kind of rain is actually called blood rain in Italy. So the wind that causes blood rain is called sirocco. The same wind which is originating from Libya is, this is Libya, it is called Ghibli. And the wind which is again same but is originating from Egypt is called Khamsin. Now there is one wind which is originating again from the desert, Sahara Desert region, but it is going, towards in this direction. And here, since there's a coastal area, there's a lot of humidity in this region, and it blows off this humidity, making it a little bearable for the people in that coastal area to breathe and to live. So that is why they call this wind as doctor wind, but it is also called as its original name is Harmattan. There is a similar kind of warm wind even in South Africa here, which is also known as Cape Doctor, but its real name is Berg. An important in India, we know everybody I think must know that there is a warm wind that everybody, local wind that we all know, which is Lu. So I marked that. There is there's a wind, warm wind in China that we need to remember, which is Karaburan. So, in options, we may think that Karaburan, that doesn't sound like a name from China, and we might eliminate it, but Karaburan is from China. In Japan, there is a warm wind which is it's called Yoma. Then there is one warm wind in New Zealand that is called Nor'wester. So N for New Zealand, N for Nor'wester. In Australia, how Sir made us remember that Australia has great fielders. So a brick fielder is the wind, which warm wind, which is found in Australia. So brick fielder. Two more important winds that we need to remember are here. So there are two winds. One is it flows in the Iran area, and another one is in the Iraq area. Both of them are warm winds. The one in the Iran is Shamal, and one in the Iraq is Simum. Now, how we remember is that, which is Shamil and which is Simum. So, Iran is, closer to India as compared to Iraq. So, if we go from here, first that comes is Iran, and first is A, not I. So, that is why Shamil will come first as when we go from India, and Iran will come first, and Simum will come next. So Simoon and then Shamal. So these are the two winds that we remember. So I think we're done with all the warm winds. Let's check out the list over here. Let's see if we've missed out on anything. So we did Karaburan, which is in the Gobi Desert region, China. Nor'wester, Brickfielder. Then we did Yoma, we did Berg, we did Harmattan. Then we did Khamsin. Oh, did I wrote Khamsin, but it is Khamsin. So Khamsin, there's Ghibli, there is Sirocco, there is Fawn, there is Santa Ana, Black Roller, Chinook, and I think we've done, okay, there's one more which is Zonda. So Zonda is a warm wind that is found in the Argentina region. So right here in this area is where we find Zonda. So I had missed out on that. But other than that, these are all the warm winds. Now moving on to the cold winds. The first important cold wind is right here in the Canada region. So as we all know that Canada is known for its cold weather or cold climate for that matter. So the famous cold wind in this area is blizzard. So blizzard is a important cold wind in Canada. Next is Buran. So Buran is actually found in Russia, right here. Important thing to know is that we do not have to mix it up with Karaburan. Karaburan is warm wind and it is in China, whereas Buran is cold wind which is found in Russia. So Buran is a cold wind in Russia. Another similar named cold wind is actually in the Adriatic Sea region. So Italy and Adriatic area, that is where we find a cold wind called Bora. Adriatic Sea plus Italy. So here we find Bora. An important cold wind is found in the Greece area, which is called Grigel. So, easy to remember, Grigel in Greece. There are two winds to remember in France and Spain. So one wind is actually found in both these regions, France and Spain both. So if I do it like this, this is Mistral, and one wind is actually found in Spain itself, which is Levanter. So Mistral and Levanter. And in this area, in the again in the Argentina region, so here there is Pampas grasslands, which is very popular. And this Pampas grassland, from here there is a very famous cold wind, which is Pampero. So I think I got all of the cold winds also now. Let us check. Blizzard we did, Buran, Bora, Grigel, Mistral in France and Spain. Levanter is in the southern Spain. Pampero in the Pampas Grass. No, I did not do Virasen. I forgot one in each. So Virasen is also a cold wind, but it is found in the Peru region. So right here. How I remembered is, oh sorry, I wrote the name of the country. Okay, Virasen. How I remembered this is that Peru is guava, we call it Peru in our regional language. So Peru is a fruit which I want to share with my Veera. So Veera is a brother in Punjabi. So I share Peru with my Veera, and that's why it's Veerasen. And we like it very cold from the fridge, so it's a cold wind. We don't like it like lying Peru, which is lying outside in the heat. We like it like really cold Peru, which is how I try to remember this. But even so, I forgot right now. But yeah, so these are the important local winds. So I've also marked a list over here as I went through earlier. So I'm sure that you would be able to pause and take a screenshot of it. But yeah, so we are done with the winds chapter. I've not done the seasonal winds in this area because I wanted to do it with the Indian geography bit, just the same way how Sudarshan Sir had done. It's easier to segregate in that manner. So I'll do all the El Nino and La Nina and all the phenomena, southwest monsoon and everything, all the seasonal wind bit in the Indian geography video series. So as such, I had decided that today I would finish entire climatology, but the video was getting too long, and I did not want to create such a long video because then it would be very difficult to revise as well. So I decided to break it in 3 parts. It was very impractical of me to think that I can do it in one video. I think the best way to categorize it would be that next I would do all the precipitation and the clouds and the rainfall and all of that, and in the final video I will do only the climates of the 9 climate types that we know. So in that last video I will do only that much, 9 or 11, I think 11 climate types that we know. So I'll do only that much in the last video. So once we do that, oceanology, I am not being impractical because even Sudarshan Sir has finished it in some 3 lectures, and I generally cover 3 lectures of his in every lecture. So it should not be that difficult. Oceanology I will certainly do in one video, but I'm hoping that in the coming week, even if I have to post 3 videos in the coming week, I will. But I want to finish with physical geography because I am. I can't wait to start with Indian geography, quickly, because then the time is going to be very less to finish even Indian geography. And in the month of June, I want to focus mostly on mapping. So, even if I may not make videos of mapping every week like I'm doing right now, but I still want to dedicate a lot of my time to that. So I don't have time to focus on Indian geography in the last month. I only can revise, I can't make videos of that. So that's my plan for the next week and for the next upcoming weeks for that matter. So I hope you found this video useful. If you did, please leave a comment below and give me a thumbs up because it really encourages me. I've been very encouraged recently because of wonderful comments that I'm receiving. So thank you so much for showing all your love, and please subscribe to my channel if you have not subscribed yet. So thank you so much for watching this video.